In today's video, we will be looking at problem F from Codeforces round 1055, diff 1 plus diff 2. So in this problem, you're given an array of n integers, x1, x2, all the way to xn, where xi is smaller than or equal to xi plus 1 for 1 to n minus 1. And we're also given an integer z, and then q queries. So each query specifies a range, L to R. And what we have to do is, let's consider the multiset formed by the subarray XL, XL plus 1, all the way up to XR. And we want to select a maximum size subset. Let's say the subset is y1, y2 to ym. And we want to select this subset such that for all I from 1 to m minus 2, the following condition holds. We want yi plus 2 minus yi to be greater than z. And in the problem, we say that this is the condition for this multiset y to be safe. Yes, so basically we're given a subarray L to R, and then we consider this subarray as a multiset, and then we just select the maximum size subset that is safe. So this is the problem. If you want to think of how to solve it, you can pause the video now, and we will move on to the solution in a moment. So to build intuition on how to solve this problem, let's first imagine we can afford a linear time solution per query. For convenience purposes, let's assume that L equals to 1 and R equals to n. So let's just solve the problem for the entire array, basically. So let's say we fix a starting element. Let's call it xi. So if we start from this xi, what could the next choices be like for this maximal safe subset? Because the constraint that we're given, which is yi plus 2 minus yi as I was said, this constraint only links elements that are 2 apart. So for the next elements, we don't really have any constraint, right? So in fact, this element only gives a constraint of the form among the elements with values xi plus 1 to xi plus z. We can choose at most one element from here. But that's basically saying for the next element, we don't really have a constraint. We can choose it from anywhere, but we cannot choose more than one from the range xi plus 1 to xi plus z. So yeah. Okay, so the next question we have is, if there are 2 elements, let's call them elements A with value A and value B. They both lie between xi plus 1 and xi plus z. Which one do we choose? Choose A or B? So in order to decide whether we would choose A or B, a helpful way is to see what would each of these choices bring us in terms of like constraints for future elements of this multiset. So if we choose element B, then this introduces a new constraint of the form. Okay, let's use the same color for consistency. From the elements b plus 1 to b plus z, there could only be at most one element. So there could be at most one element with value between b plus 1 to b plus z. If we chose A, however, then we're basically saying that among the values a plus 1 to a plus z, we can at most choose one element. Okay. By the way, just to be clear, a and b here refer to values, not indices. Okay. So, but basically, we have two types of new restrictions that we care about here. It's either one element between b plus 1 to b plus z, or one element between a plus 1 to a plus z. So which one do we prefer here? It is not hard to think that we would prefer having a constraint that is more to the left in the number line. So why is that? It's because we already have a constraint of the form there can be at most one element from the range xi plus 1 to xi plus z, and we already have chosen one element here. So naturally, we cannot even choose anything up to xi plus z, right? So we can discard all the restrictions until we are here. So everything before xi plus z now does not matter anymore. It does not matter. So we're only looking at these two new restrictions, one of which is actually a superset of the other one, right? So for the restriction of B, it extends longer than the restriction of A, and therefore we would always prefer A over B. So in general, we would always want to choose the next element based on its value. We want to choose the element with the smallest possible value. And in this problem's case, it's very convenient because the array is sorted. So this translates to we want to choose the next element with smallest possible index. Okay. So basically, what this tells us is that if we start with element xi, the next choice must be xi plus 1. So what about the next choice after this? You might say, okay, we want to choose the next element with the smallest possible index, right? So it must be xi plus 2, right? So it turns out that this conclusion is wrong, because if that's true, we could just select the entire array, right? We still have to fulfill the condition that for every two elements that are 2 steps apart, their difference must be greater than z. So here we're actually selecting not xi plus 2, but some xj where j is the smallest index greater than I, satisfying, actually it should be I plus 1, satisfying xj is greater than xi plus z. So that is how we choose the third element, and for each subsequent position, we would use the same algorithm. Basically, we would look at the elements that is the current second last element, and then we would find the smallest index that is greater than the previous element, satisfying this element is greater than the element that is 2 elements before, so the second last element, plus z. So that would be our algorithm. The remaining question here is, okay, so we have almost solved the problem for a single query. So the remaining question is just which starting element to choose. So from our discussion from from our discussion so far, it is pretty obvious that we would prefer earlier elements in general. So we prefer elements with smaller index. That means, given query L to R, we would start with index L. And that is because earlier elements give us constraints on future elements that are smaller. So basically, if we start from L, our first constraint will be of the form xl plus 1 to xl plus z. And in this range, you can only choose one element. Yes. So in conclusion, we would always start with L, and then L plus 1, and then we'll continue. Yes, so basically this is how we would solve the problem for one single query. We would start from the index L, and then we would go for L plus 1, and then we would keep going for an element that is the smallest index that satisfies the value of this element is greater than the current second last value plus z, and that would be how we solve one query. Okay, so moving on to implementing this greedy algorithm efficiently. So how to solve for multiple queries is the current problem. Let's say we fix a query LR, and we would define a function bi for some index I, where bi is the minimum j such that j is greater than I and xj is greater than xi plus z. And that's exactly what we were looking for in the previous section, right? So we're looking for the smallest index to the right whose value exceeds xi plus z. And if this index might not exist, so for convenience we could assume xn plus 1 equals positive infinity. So if this index does not exist within x1 to xn, then bi would just be equal to n plus 1. Okay. So for a single query, we would start with the two elements L and L plus 1, right? So or maybe we could write it somewhat in the middle. The first two elements, the first two indices, these are all indices, would be L, followed by L plus 1. Yes, so what would be the next value here? So we're looking for an element that is okay. So for the next element, we want it to satisfy xj is greater than xl plus z, and j has to be as small as possible. So naturally, we would want to link this to BL, right? So we would naturally want to link this to BL. However, there is a slight problem here. What if BL is equal to L plus 1? So if BL is equal to L plus 1, then that means we're actually deciding that the third element of this sequence should be L plus 1, but then this multiset cannot contain elements with the same index, with the same indices. So in fact, this is not possible, and we cannot set BL to be the next index for sure, right? So indeed, this is a special case which we would currently decide to not consider. Let's skip this special case for now. And let's just assume BL is not equal to L plus 1. And of course, it would be greater than L plus 1 in this case. Okay, so that means the third element would be B of L. So what would the fourth element be? So we know that L leads to B of L, as the first element leads to the third element. So similarly, for the fourth element, we want to look at the second element, since it's currently also the second last element. So we want to find an index such that x of that index is greater than x of L plus 1 plus z, which might make us think of B of L plus 1. So here is another question that arises. What if BL equals to BL plus 1? So indeed, this is another special case which we would currently skip, and we would come back to this later. So for now, let's assume that BL is equal to B of L plus 1. And we would just assume these two conditions in general as well. So assume Bx is greater than x plus 1, and Bx is equal to B, oh, there's a mistake here. Assume BL is smaller than BL plus 1, and assume Bx is smaller than Bx plus 1 in general. Okay, so if we have these two assumptions in mind, then how would the sequence continue? This sequence would continue as follows. So after the two elements BL and BL plus 1, the multiset would move on to the fifth element, which is B of L. And then the sixth element would be B of L plus 1. And then we have B of L. We'll just abbreviate that with B cube of L, just like function composition. So here we have B3 of L plus 1. Yes, so do you see the pattern here? We're actually decomposing this entire, this multiset into two separate chains. The first chain being L to BL, to B of L, to B of L, and so on. And the second chain goes from L plus 1 to B of L plus 1, to B of L plus 1, to B of L plus 1, and so on. So these two chains are sort of independent of each other, which is not true for the actual problem, since we have assumed these two conditions over here. Since we have these two assumptions, we can really turn these two chains independent. So we only need to consider L, BL, BBL, and BBL, L plus 1, L plus 1, and so on and so forth. So obviously we would continue these two chains until one chain enters a value that is greater than R. And once that happens, we would terminate the entire process, right? Because once it is greater than R, we would not have to consider any future elements. Yes. So with that in mind, how would we be able to solve this problem efficiently? So there's a standard technique to do that, and it's called binary lifting, which I will not go into too much detail here, but basically it allows you to find how many elements are there before we arrive at an element that is greater than R. And we can do that in O of log n time. Yes, so basically for anything that involves applying the same function, or applying a same, in this case it's applying the same function many times, then we can speed it up using binary lifting, and that would achieve logarithmic time instead of linear time. So it remains to deal with these two special cases. We can consider, let's say the sequence currently is some elements followed by x and y, and x is the second last index, y is the last index. Okay, so we can actually write this special case a bit more generally. So we're considering whether or not the next two elements of the sequence can be b of x and b of y. So we would like to consider special cases where bx equals to y or bx equals to by. So that's the general version of these two special cases, and we will now see how to handle them. So the first special case, bx equals to y. So if bx equals to y, what would be our sort of like a replacement sequence for this sequence? So it's no longer bx and by, right? So instead of bx and by, our sequence would look like that, x, y, and then this would be y plus 1. Okay, good. So what about the second special case? The second special case is one where bx equals to by. So the sequence would look like the following: x, y, and then, well, here bx is no longer equal to y, so we might as well just have bx. But then since by is equal to bx, we cannot have by here. Instead, we could have bx plus 1. Because of the same reason, we know that bx plus 1 must be a valid element to exist in this sequence, and it is greater than bx, so we could choose bx plus 1 instead. So now we have observed how the sequence could look like in these two special cases. Do we observe a pattern here or some similarity between these two cases? And it turns out there is some similarity. So in the first special case, our sequence actually passes through y and y plus 1. And in the second case, it passes through bx and bx plus 1. So the similarity here is that it passes through elements with index difference of 1. So y and y plus 1 are just one index apart, and bx and bx plus 1 are similarly also one index apart. This prompts us to arrive at an algorithm that is based on these pairs of elements with index difference of 1. So how can we make use of them? Remember that we start our sequence for any query. So like for L to R, we start our sequence by the pair of elements L, L plus 1. Right? So the first two elements must be L and L plus 1. So this is obviously going to be important, but then we now know that for any starting point of a sequence, we might eventually end up in these two special cases. And in these two special cases, we will need to handle them by these special values and bx plus 1. So what's going to happen is that we will simulate what happens when we toss L and L plus 1 in. So we would figure out at which point. So obviously, if there's no issue, the sequence would go on as normal. And it would go like that, it would go like that, and so on. So this would continue forever until we arrive at some index where a special case arrives. For each I from 1 to n, store a special array. Let's call this array, let's just call it P of I. If we start from I plus 1, how many moves until we meet a special case, and which x is it such that the sequence passes through the elements x and x plus 1. So this might be a bit difficult to understand, but basically, if we know that from I plus 1, we would be able to keep doing this function composition thing. So we can continue following these two chains until we arrive at a special case, which is defined by either of these two conditions. So if we meet a special case, we would definitely be able to meet a pair of consecutive indexes, right? So in the first special case, we would meet y and y plus 1. In the second special case, we would meet bx and bx plus 1. So in this case, what we're going to do is go from I to x. It's kind of like a fast forward process. So obviously, this would store an information in the form, how many moves has passed. Before I could go from I plus 1 to x plus 1. And here by moves, I mean how many elements have we added to the multiset. That's basically the same thing. If we were thinking it from a binary lifting perspective, or like a graph traversal perspective. Yes, so that's basically how this algorithm works. We would code two separate binary lifting. So the first one is for this basic function composition. So we will just assume that there is no special case. And if there's no special case, we can obviously solve the problem in O of log n time, right? So the second binary lifting would be to deal with the special cases themselves. It would be the form. For each element I, we compute, if we start from I plus 1, how many moves until we meet a special case. And for this special case, which x is it, such that we would pass through the elements x and x plus 1. So that is basically the second boundary lifting. And we could just jump through this graph until we meet something that is close to R. And then once we meet something that's close to R, we could go back to the first one, where we guarantee there is no instance of a special case. So if there is no instance of a special case, we would safely just compose the function until we enter a value that is greater than R. So that is basically how the solution to this problem works. So please check out the implementation to this problem in the next video. I hope you enjoyed today's video and found the problem interesting. If you like this video, be sure to comment, like, and subscribe to my channel. Feel free to suggest problems that you want me to go over in the comments or in the opinion box, link in the video description. Thank you for your support, and I'll see you in the next video.